and we can start letting people in.
Okay, so let's start for today. First, thank you very much for everybody joining. Usually, Joanna is doing the introduction, but she apologizes for not being able to join today. So I'll take over the baton for the day. And I promise I won't take too much time for the introduction, but welcome to this fourth webinar of our second semester of the Space Economics Seminar that we're jointly organizing between Harvard Business School and ESPI, the European Space Policy Institute. One of the biggest reasons for why we started this was because we realized there are not many economists who are dealing with economics of space, with economics of space activities, and a lot of the discussions and also programmatic action surrounding space activities, both in Europe and the US, is sometimes foreign to those discussions on economics. So this initiative tries to fill that gap and provide a platform to economists and to also encourage economists to write about space activities. And I'm sure that we'll see more of that in the future. But for today, I'm very excited to announce the presentation of Oğuz Karasu, who is a postdoc researcher at the Said Business School of the University of Oxford in the United Kingdom. The topic for today is an economic impact analysis for space-based solar power systems on the world's economy. The paper also was attached to all those attending in the invitation email. But without further ado, I pass on the floor to Oğuz and look forward to his presentation. I understand his colleague Maria will also jump in with a few comments and inputs from her end, as she's one of the co-authors. Looking forward, and the floor is yours, Oğuz.
Thank you so much for your kind introduction and also for the invitation. Hi, everyone. I hope you're all doing well. We're about like 30 people. So let me start my presentation and share my screen. And then we can start. So can you see that? All good? Perfect. Okay. So before I start my presentation, I'd like to talk about the story of this paper. So Maria is my colleague. So we met through her professor Moritz. He was also the part of the paper. He is professor of physics department, and he's working on like solar panels, etc. And I was thinking and working on the space-based solar power systems and their economic impact at that time. And then we combined our studies together, and based on Maria's studies on OPVs, like possible technical opportunities for space economy. So let me share my outline real quick. So since it was the last minute invitation, I just like quickly prepared a short presentation. So I will talk about the space-based solar panels first, and then the difference between silicon-based solar panels and also organic photovoltaics. I hope I'm not wrong about the technical details. And then Maria will step in about methodology, data, and some of her assumptions and also findings. And then we will talk about the macroeconomic implications of these projects and also about the results. So let me quickly talk about this space-based solar power. I took this graphic from ESA's website. So basically, it is a system that we deploy to orbit, collect this sun's power through the panels in orbit, and then with some technology, which usually it is right now the microwaves, to send it back to Earth and then distribute to the all CDs electrical systems. So this is the main idea. But while I was thinking about like every other project in space industry, the possibility of these projects, I was thinking, okay, like what is the main approach from the government and also from the company side? Because yes, there are some companies who are working on these solutions, on these projects, but I haven't seen anyone who like efficiently deployed those systems in orbit and start like, capturing the sunlight and then send it back to Earth efficiently in a profitable way. There are some tests. I believe the latest tests either has been done or will be done by Japan. I think Ohisama project. So they sent the test satellite last year. So they are planning to do the test this year, I hope. So, and there are also some government initiatives, but mostly what I realized in the past, most of the companies they're focusing on creating the technology, but all those systems are based on Starship's success in the future. So they created their business models based on Starship's success because the current technology, the silicon-based PVs are very heavy, and to be able to capture the sunlight in an efficient way to beam back to Earth, you need like a very large constellations. So you definitely need something to launch like Starship. So without Starship's success, unfortunately, I don't think we will see any current company's success in the near future. So let me continue with the this study's base base assumption. Maria did a computer-based test um, between silicon-based solar panels, and organic-based photovoltaics. So the main difference between these, of course, silicon-based is inorganic. They are very efficient. They are heavy. Lifespan is very long. And organic photovoltaics are very light. They are not as efficient as the silicon-based ones, but they're super light, and lifespan is not that long, but still workable, and also the performance is excellent in theory. So, Maria, would you like to step in and talk about your assumption, your approach, and maybe we can continue with the rest of the graphics? And also, you could
Yeah,
please introduce yourself as well.
sure thing. Hi, everyone. Hello, my name is Maria. I did my studies for my master's in Oxford with Professor Reed. His main focus was organic photovoltaics, and this whole thing started by looking into potentially space-proofing OPV to be used in space, and from there, it was just all of the different applications we could be using it for. Space-based solar power starts as a main use for OPV because it's kind of like a perfect use case. You would have a lot of area, and you would require a very thin and low weight material. So that's why we're thinking of, okay, what would actually mean for us to be looking into it. In terms of the methodology of how this techno-economic analysis functioned, is I first looked into the lab properties of OPV. OPV has not been space proofed, and so we don't really know how it's going to behave in space. So we had to just get as much information as possible. So in the short time that I had to do the tests, focused mostly on two, which was thermal and radiation testing. And from there, we used that information to, as August said, create a Monte Carlo analysis that would look into a version of the levelized cost of energy. I don't know if you guys are aware of the levelized cost of energy, but what that does is
I put this graphic, Maria. Maybe this will helpful for you to explain.
Yeah, thank you. So this one overall just shows the installed capacity of PV versus the cost of PV. So as we can see, the cost of like normal photovoltaics has decreased quite a lot, and then that has made it so it has just had more installed capacity. This talks mostly about silicon-based photovoltaics. There's plenty of other technologies, but yeah, just overall, that's where we're at. OPV is more of a new technology, is not that commercially available overall, but it has a lot of potential use, particularly for space. As August was saying, the biggest cost in terms of space-based solar power, as shown by our paper and our research, has shown to be launch, and launch is directly related to mass. So there's definitely a trade-off in between efficiency and mass that you would want to get to. And that's, I think, the biggest take on this approach. So yes, as I was saying, like the thing, how it worked is levelized cost of energy. What it does is it helps you quantify the actual cost per megawatt hour produced by different technologies. So it's something that is done on Earth for every technology. We know the comparison between hydroelectric or photovoltaic or nuclear, etc., etc. What we did is look at that and then transform it into what I called the levelized space cost of energy, which looked into items that the normal LCOE does not do. So the levelized cost of space energy, I kind of increased the formula to take into account space-specific items of economy, such as particularly launch. So it was particularly launch would go into the CapEx, and then we already have maintenance into the OPEX cost. But it's a different type of maintenance here, given that it would have to be done in orbit. So it's how much of it can you do, and how much of it you would just have to assume that the maintenance cost will have to be zero, but then the efficiency of your technology will decrease. So again, it's a trade-off of how much can you actually get done in space versus how much will you want to be spent on whatever you're doing. So what we done is we run 4 different scenarios, 2 for PV and 2 for OPV. And this could have been done with different technologies. We just chose PV as a technology that has been done and tested, space tested. We know how it behaves. We know what to expect of it. We also know that it's heavy, particularly crystalline silicon one, which is the biggest one that's used right now, versus a new technology that you have less information, that it may fail, that the conversion efficiency is not that good, but has storability capacities. So you can roll it and then you can deploy it, similar to what you can do with lots of different satellites that you've seen. And most importantly, it is very, very thin, and therefore it's extremely lightweight. And I mean, yeah, the results kind of speak for themselves. What you're seeing there is the levelized cost of energy per the different scenarios, with the error bars being PV, the most expensive one, and then OPV, the less expensive one. The different scenarios, what we've done in terms of each different one, it's just a current power conversion efficiencies. So I used 10% and 20% for scenario 1 in terms of OPV and PV. And for scenario 2, it's the future assumed efficiencies. So we would go to 30% roughly for OPV and 40% for crystalline silicon. That's why you can see that scenario 2 is significantly cheaper for PV. However, in terms of OPV, that conversion efficiency increase is not that important anymore, which shows that overall the main cost driver will be launching. And that's what August was coming into in terms of this is all well good and tested. I'm not an economist, by the way. I'm an engineer. I'm into physics. But even a non-economist like myself can tell you that like the main cost driver for these technologies and for this line of exploration is linked to launching. So yeah, August, I don't know if you want to.
Yeah, sure. Thank you so much, Maria, for all the details that you have shared. As she mentioned, this hasn't been tested in real life. So if there's any investors between the audience, if you want to invest into Maria's project, please send her a message. And I believe like this, if this will be tested like on orbit with a real experiment, I think the whole energy sector will change. So I did another paper. I wrote another paper about the comparison between space-based solar panels and solar farms on Earth. So probably you may have heard like there are some reports like in the internet made by the consultancy firms. They are kind of pro of these constellations, like current solar space-based solar panel systems. I'm not against them, but I just wanted to approach from a rational level because the current costs that's coming from the launch providers or like other maintenance issues showing us that is not profitable. And some of the reports are saying that they are expecting some, like decreased cost from technology level, either from the launch services or from the solar panel systems. But still, until 2040, we won't see a major change if we won't see this kind of a different technology being tested and maybe in use. So this shows us that we should approach these kind of like space-related projects very carefully, because if we don't count every element in a rational level with other aspects, at the end of the day, we will lose money, time, and energy, which are the most important things in our lives right now. And also, I have to mention, if, for example, if this OPV, like a new technology, will be used in these systems, and that we can see that those are working, so if we deploy them and if we use them, we will see a different economic system on Earth as well. So basically, we will have a simple way of getting electricity for rural areas. We won't need to build like a complex systems on cities as well. So we will be able to send electricity anywhere on Earth, right? So and those are also like aligned with the UN's the SDGs, right? Sustainable Development Goals. So we will see actually major changes in our economic system if these systems will be eligible and profitable in a short term with eligible technology. So let me continue with this. So macroeconomic implications, briefly from our study, I can say for the conventional systems, the cost is exceeding 1,000, right? Megawatts per hour, I believe. And with these like computer level tested systems like OPV can be between like 53 and 100, 160, we can say. So all like between 20x and like 10x, this possible system, this alternative system is more profitable than the conventional one right now that they're promising for. So I believe like this is like highly significant, so and worth to try to test and see, because my biggest concern is, okay, we are hoping that Starship will be successful very soon, right? Especially for these space-based solar panel companies. But what if it won't be successful for the next 10 years? What will happen to those current companies that are working on space-based solar panels? So most of them, they will be bankrupt. Even like governments cannot wait or invest into those companies without seeing the like real results of these technologies. So that's why I've realized there are three critical areas that we need to focus for our future work related with these technologies. First, achieving substantial reductions in launch costs. Yes, this, like I mentioned. Second, conducting rigorous in-orbit testing with these technologies, with Maria's lead, hopefully. And also third, the holistic models that integrate generation with transmission subsystems, such as Rectana's satellite infrastructure to present a complete picture of BSP's feasibility. So these efforts will be instrumental in transforming these systems from a theoretical concept into the future global energy landscape, hopefully. And the last thing, so this is not just a technological innovation in my perspective, but this is an economic paradigm shift if these systems are technically possible. And the strategic advantages beyond the energy generation, supply security, geographic independence based on these systems. But also we will face with the problem of space debris in the future for these technologies, because we all talk about the increasing number of satellites. There are 12,000 right now, and we expect many more coming from SpaceX, and China just announced they are planning to deploy 100,000 satellites. So that means we will definitely see space debris problem, and space debris problem is actually affecting these systems directly. So we have to consider all these like aspects on Earth, manufacturing level, supply chain level, and also in orbit from space industry level. So without these limitations, our approaches, our projects, unfortunately, won't be real, and also they will waste our times and resources, which are the most important thing for the economics studies as well. So thank you so much for listening. That was a bit short presentation, but I also wanted to discuss, because this is my current opinion, and I am open to change it. I'm open to develop it with the criticism, with real questions, with real you know opinions. So happy to discuss more, and I believe like Maria also will be very happy if there is like any positive criticism and or investment possibilities. So happy to listen from you guys now. And I couldn't add any references to the presentation, since all of them are in the paper. You can reach them from there. Let me stop sharing that.
Perfect, thank you. And as it's usually the case, all questions are of course more than welcome in the chat, but also you can raise your hand directly, and we'll spotlight you and provide you with an opportunity to provide a comment or a question to Oğuz and Maria. Maybe to start off, the question when it comes to the question around when it comes to space-based solar power is like, of course, there is one part of the question which is the technical feasibility, and I understood this is also something that Maria is working on. But there's also, of course, the investability, and when it comes to a question such as sort of power grids and also electricity markets on Earth. What have you looked into what would be the sweet spot between the technology development and the technology maturity that is still necessary, but at the same time also what is sort of the timeline, the feasible timeline for investing into such a project such as space-based solar power? So what would be the time frame of investment that a private investor or an institutional investor would need to sort of commit to for something like this to become reality, if the technical feasibility would hold up?
Yeah, great question. Thank you. So I did an analysis about that, and I've seen that like at least 10 to 14 years right now, if Starship will be successful. So this is very long. And when I compare this with solar farms on Earth, there are some countries, if you invest into solar farms with battery storage options, you have your money back in 3 years maximum. So you know what I mean? Like it's a great investment. Like there are not many like investment opportunities like that, like this on Earth either. So when we compare two systems on Earth and on orbit, in orbit, like the difference is huge. Like Maria, if you have any comment, please like share that as well.
No, I would agree with that one. And then another thing to note, for example, for my analysis in terms of survivability as well, it was based on a 20-year mission. But there are plenty of other things to note. So something, apologies, I don't think we mentioned is in terms of space-based solar power, at least the version that we're looking into it, we're looking for it to be done from geo, because then that would mean a virtually 100% power throughout the year. And when you're talking about 100% of power throughout the year, that is, you're talking of base load power generation and firm power. Then other items in terms of economy also start coming into place, because as more and more we walk into lower emission and net zero, etc., and we want higher integration of renewables in the grid, we will need to have more baseload power that would then allow you to have that renewable integration of, say, wind or terrestrial solar that you can't really control in terms of when you'll get the resource, and if you'll get the resource. Or for solar, for example, then you're obviously at night, you'll be limited. So there's also some ancillary services to consider that are becoming more and more important in the market in terms, for example, of like harmonic filtering and making sure that we've got enough generation to match the load. So there's also that immediacy of being able to say, okay, we're able to follow the curve of generation throughout the whole face of the planet. So say, for example, if you've got space-based solar power that would benefit the UK, it would also be able to benefit all of Europe. So you could be following that curve of generation and consumers throughout Europe and saying, okay, well, if you are have higher energy prices in Germany at the moment because you've got more people that are using electricity there right now, then you can shift it to be there and then kind of just like go around until you reach to the end of Portugal, where like people go to sleep and then prices go down. And I work in transmission distribution at the moment, and that is something that I'm looking into right now, of seeing what implications something like SVSP could have into the actual market, not only in the UK, but in the world in general. And that is an area that I think economists should really look into as well, because the more that it gets into more and more renewables, the bigger the problem in terms of not only cost, but also like technical capabilities. So yeah, right now we've got some options in terms of nuclear or hydroelectric, but it's limited.
Perfect. Thank you, Oğuz. Maria, I see there was a question raised by David in the comments. David, do you mind bringing up the question via video? Perfect.
Sure, I'm happy to. First of all, thank you both for the presentation today. It was very interesting to read your paper. The problem of dependency on SpaceX ship continues to be one for many firms, especially a concern here in Europe. And so what my question was, and throughout your analysis, I'm wondering whether you have identified that ceiling in the launch costs at which that even the most efficient OPV scenario becomes uncompetitive. Because I'd love to see that we can still get there without that one dependency.
So actually, in terms of my analysis, that's why I did not want to use SpaceX only. So I don't know if it's into the paper or not. It's definitely into my dissertation. But what I tried to do, and that's also why I wanted to go with the route of a Monte Carlo analysis and not just using base costs, is exactly because of this that you're referring to. So there's a table, I'm pretty sure it's also in the paper. If not, it's definitely in my dissertation. I can share it with you, of all of the different launch vehicles that I looked into. And what I did is I compared the average cost in terms of millions of US dollars per payload capacity to LEO. And so what you'll find on the results that we've presented, those are not only not based only on Starship. Those are based on current technologies that work. That's also why the PV section is so high, because I did not account for a future launch vehicle that sounds amazing, and we all hope that it can happen, but it's not a reality right now. So that graph that you saw in terms of the 4 scenarios, that's with current technologies that have been done and tested. So that's like SpaceX Falcon 9, Falcon Heavy, ULA Atlas V, Arianespace Ariane 5, and Rocket Lab Electron, I believe, were the ones that were accounted for.
Well,
Great. Thank you.
Thank you, Maria. From economics point of view, I completely hear your concern. And my comment is on that, like, yes, costs are decreasing per se, but sometimes price is not as cheap as we think. So especially when you like launch satellites or things to up there. If one person cancels, you have to pay the rest of the cost. So it's not like yes, cost is down for the company for sure, but we don't know how much they charge each time. And since they become like kind of like monopoly, like it's becoming a problem for the space companies and also for the governments. So that's why I try to like encourage the launch companies in Europe work harder and like get there, because like at the end of the day, SpaceX is dominating the market, and if Starship will be successful, yes, it will be cheaper for sure. But I believe we don't know whether there will be like regulations that are limiting our launch intentions or not. So those are going to be major questions in the future.
And sorry, just last thing there, but that's also why looking into non-traditional technologies is so interesting as well, Because if you were to think of this as a just a traditional silicone technology, for example, it would most likely mean that you would have to do the assembly in geo, which is quite far away and quite difficult. However, if it's something that you can do with a deployable, stowable technology, say OPV or any other flexible solar panel, then it's something that you could do in a lower orbit and have ready to be just deployed once it reaches higher orbit. So that's where different things come into place, and it's a matter of just finding efficiencies in every single item of the design, not just in one of them.
Speaking to that efficiency, I actually have another question, but I'm happy to cede the floor to anybody else. Then I will continue. In your sensitivity analysis, were you able to identify to basically at which point of degradation would that threshold of annual efficiency loss is going to be negated by the cost of frequent maintenance or replacement? Obviously, the timeline there between these two are very different, as you highlighted. And so I can see where the cost saving are there in terms of even with the lower efficiency, but is there a point where that stops being the case?
So because of us not really knowing how OPV would behave, I gave it a higher yearly degradation, but I also gave it a higher sigma in terms of the variability. So what I did there is there was a mean degradation of 1.2% per year with a sigma of 20% for PV, whereas OPV, it was mean 1.35 with a sigma of 35%. And even with that, then you can still see that the cost stick. And again, I based those on lab tests that I did in terms of thermal and radiation cycling. However, it is true that there's lots of things that you don't know. And that's why Oğuz was saying that it is so important to just be able to actually test these technologies with a multi-environmental test in space, say it CubeSat or say it any other sort of mission, then that would be better. In terms of being able to give maintenance to it, then that becomes a little bit more complicated. Because the main thing that I would say there is we go back to the design of what we were talking when I was saying like it's important that you design something that you could then do there. Because then what I would potentially prioritize and what it was prioritized overall is to make sure that the satellite that you have in mind is just there are different units that work together instead of one system overall. Because then if there's one unit that there's, I don't know, say like there's a plasma bit that goes wrong and an area short circuits, you still have the rest of it that works. So that's another main thing to account for. And that's also something that it would be very interesting to do in terms of what's the biggest item that could take out a satellite or that could take out any sort of space infrastructure, and how can we build around it. The fact, for example, that something like OPV has bigger stowability and low mass per megawatt hour produced allows you to then be able to use other technologies that would protect in terms of, say, that electron fluctuation. That could potentially mean that, if anything, you could make it more resilient towards space, not the other way around, because you have that extra jiggle point of saying like, oh, it's less heavy, so I can engineer more things around it to protect it. Whereas the other way around, it's more like it's already too heavy. I can't really put anything else to allow me to protect it.
Perfect. Thank you, Maria. Thank you, David, also for the question. I see another question was brought up by Johnny. Johnny, do you mind bringing that up via video following David's example? If you are still
Sure,
perfect.
absolutely. Hi, August. Good to see you again. Yeah, just I guess building on the previous comments on launch vehicles. I guess there's a more macro question I'm thinking about, which is what happens going forward a few years out, where just the promise of space-based GPUs and data centers seems to be trending on the news right now, and with the power energy capabilities you've discussed with solar panels. But leading up to that, kind of what happens 5 years out from now? Is there going to be a bit of kind of blocking from the guys that have mastered the commercial launch space, or is there going to be like more and more capacity for new entrants to build their own launch providers? And from my initial research, the fun fact I learned was Rocket Lab and SpaceX, they took about 7 to 8 years, about 30 to 40 launches to successfully master the reuse. So what does that lag period look like, etc.? So if you have any thoughts on that, I would appreciate that. Sorry, August, you're
August.
on mute there.
Thank you. Thank you so much. Yeah, thanks, Johnny. I have a joke. I usually say this like in the panels. So, economists, they predict the future, and then it most of the time it doesn't happen, and then they come back and then they say why it didn't happen. So in 5 years, if it won't happen, like I will come back and say why it didn't happen. So that's how I earn our money. But from the launcher perspective, as you know, these companies, most of them, are backed by the governments. So they are government contractors. Without their support, they wouldn't be that much successful. That's for sure. That's because also these technologies are eligible for dual use. And governments, especially America, they want more options. So they want SpaceX to grow, but they also like create their own solutions like SLS, right? They just tested it with like humans inside. So SLS for moon or like further missions for planetary missions. And Blue Origin is also like supported by the US government. So it is highly like the technical difficulties for launch capabilities are like super high. And without government support, I don't think it is easy for anyone, even for Europe, to create these kind of like capacities for the like near future. And other thing I was going to say, um, you mentioned about the data centers. Yes, so when I first started to do research about space, I saw a lot of space mining, space tourism news. So that caught my attention actually at first, like 9 years ago. And but they're still there. We are still talking about space mining, we are still talking about space tourism, but they are not the major activities. And in my belief, since it is not like in public yet, the data centers are just a discussion to catch the the general investors' attention for space by Elon Musk. So I don't think it is a profitable way of growing, having space like data centers in space, because it is not like space-based solar panels. There are some technical problems with the concept, with the idea of it, because anyone can come and capture your satellite with the current technology. So I spoke with someone who built data centers on Earth, and we were discussing this issue with him. I said like this is not profitable yet, and said no, it's a brilliant like idea. I said like, do you have security like in front of your data center on Earth? Do you like build walls and doors and do you lock them? He said yes, of course. then why you don't do that for for data centers in space? Like it's not possible yet. So there has to be some some real solutions for those problems. But for now, that's just an idea, and we can discuss this as well with the audience.
Perfect. Thanks for the question, Johnny, and also for the informed answers, always, Maria. I don't see any additional questions in the chat at this stage, and we are right at the 45-minute mark, which is usually the academic hour in Europe. So maybe the system self-regulates itself. If no further questions will be coming in over the next minute or so, I would like to first thank Oğuz and Maria for their presentation, also for sharing their paper and for submitting it to the Space Economics webinar series. Also to all the attendees, you are very kindly invited to join us for the last and final session of this semester, which will take place on the 29th of May. The speaker will be Akhil Rao from Rational Futures, previously also chief economist at NASA. I think he was also here with us today in the meeting. The title will be Cost-Benefit Analysis of Debris Risk Reduction Portfolio. So going from space-based solar power, and we ended up with space-based data centers, but all those sort of launch activities and operations in orbit, of course, also create debris-related risks, and looking forward to hearing from Akhil on that part of the economic spectrum, on his latest analysis and his latest research. Indeed, David, that's Friday, the 29th of May. So in this specific case, it won't be a Tuesday, it will be a Friday, 29th of May. But Emma will also be reaching out to everybody with the invites and also the relevant inputs and papers in due course. If that is all, I would also like to thank our Harvard Business School colleagues, in particular, also Tony and Emma, as well as Ninhe. And I think Matthew couldn't join us today due to some professional commitments, but he'll be back with us on the 29th as well. And last but not least, of course, once again, a big thank you to all the participants and the presenters today. Thank you so much, and wishing everyone a great remainder of the week.
Thank you.
Thank you very much.